All right, well, we're taking a look at section 1.7. And what we're getting into are intervals and inequalities. And so first we're going to go over is, well, what are intervals? What do they mean? So let's say we have something like this. So we'll start out with intervals. So in this text, you'll see parentheses. What these mean is that we're not including a number. And not just a number, but also we don't include infinities also. And then when you see a bracket, that does mean to include that number. Now, you won't see these on infinities. We don't include infinities because infinities are really a concept. They're not really a number. And so we're not going to include those. And so we'll exclude the infinities, and there are some numbers we'll exclude as well. So let me give an example. Let's say we have this. Now, what this means is we have an interval from 1 to 6. So all the numbers from 1 to 6. And we're not going to include 1, though, but we are going to include 6. So on the number line, what this means, we have 1, we have 6. So what we would do, and let me grab a pin here, we're going to include the number 6, but we're not going to include the number 1. So that means this interval will be all the numbers 1 to 6. It will include 6, but it's going to exclude the number 1. Now, 1.0001 will be in here, but not 1 itself. Now, what this looks like in what we call roster notation. It's all numbers x such that x will be between 1 and 6, but we do include 6. So x could equal 6, but it's not going to be equaling 1. So that's the roster notation version of this interval. Let's take a look at some other intervals. To infinity. So we're not including 2. We're not including infinity. Now, what that means is that when we don't include infinity, it doesn't mean we're going to refuse to keep on going. We're still going to go on and on forever. You never actually get to infinity. You're just going to keep going, going, and going. So we always exclude it, but really we're still saying keep on going down in that direction of that number line. So what you'll get, here's number 2. And so we want all the numbers really just bigger than 2 and just keep going on and on and on. And then we're not going to include 2. We're going to leave include 2 out. So we're going to get something like this. Now in roster notation, what this looks like, it's all real numbers x such that, and again, that bar just means such that. And now we describe what x is. Well, x will be some number greater than 2. So just a quick review on roster notation. We use it like this. This is the object we're talking about. and this is such that, and this is the properties of that object. For example, I'll give you a little more complicated one. Let's say the rational numbers. So with rational numbers, it's the set of all fractions. So it's all numbers that look like this. A number over another number. So this is what this element looks like. Now, we're going to describe the exact properties. There's a few things we want to clarify. First off, A and B are integers. So that's a property of this object. It contains integers. And B can never be 0 because we don't want division by 0. So again, with roster notation, this is the object we're talking about, and these are properties of that object. And this ultimately is a set. So any elements in this set must be this kind of element with these kinds of properties. For example, 1 over 2 would be an element of this set. This means element of. Because 1 and 2 are integers, and 2, the bottom numbers, not equal to 0. So this would be an element of this set because it's this type of element with these properties. Integers, specifically not equal to 0. Now something that wouldn't be in this set would be something like this. This is actually undefined. But this, just as it is, okay, these are integers. It is an integer on top of an integer, a over b, but the b is equal to 0, so this would not be an element of this set. So that's the idea of roster notation. So what's happening here, the elements in this case are sort of simple. They're just some number. We don't know which one exactly, so we'll call it x. We could have called it n or y or anything. And then the property of one of these numbers, it has to be bigger than 2, and that's it. All right, so let's take a look at another one. Let's say we have this. Negative infinity, 3.5, but now we've got a bracket. So this means we're including 3.5. So this means we want all the numbers below 3.5, and we're also going to include it. So in roster notation, it's just any real number x. And the property of this real number, whatever this real number is, it's less than or equal to 3.5. And that's going to be it. All right. Now, some of these get a little more complicated. And we need to talk about what's called intersection and union. And these are things we do as sets. So first off, union. When we union two sets, that means we take the elements of those sets and put them together into one set. So if you have a shoebox full of marbles and a shoebox full of stamps, when we take the union of the two shoeboxes, we're going to put them all in the same collection. So we're going to put all the elements together. In one set. So we'll put all the elements together in one set. So what this little operation looks like, it looks kind of like a U. So for example, let's say we have this. We union that with that set. So we have two different sets, 1, 2, 3, and 7, 8, 9. So we put all those together, they'll combine into one set, 1, 2, 3, 7, 8, 9. Now, sometimes sets could overlap. So let's say we have this. 1, 2, 3, union 3, 4, 5. Now remember with sets, we don't have repeated elements in sets. Sets list types of objects. If you have a formal list, say, you could have repeats of the same object. But in a set, we only mention an object type once. So that means when we union these, we'll get 1, 2, 3, and only a single 3. Because we're listing types of objects. So we have a type 1, a type 2, a type 3. We only need to mention it once to indicate that it's in the set. Type 4, type 5. All right. So that's the idea of union. The other type of set operation we're going to look at is intersection. And this is the set of overlapping or shared elements, sort of like the intersection with like a road or something. So it's really the elements that sets have in common. So for example, and so let me give you what this looks like. It looks like a cup flipped over. That's intersection. So for example, let's go back to this one. Well, what elements are common between these two sets? Well, it's only the number 3 that appears in both sets. So in this case, the intersection just contains that common element. Or another one, say we have this. So what elements do these two sets have in common? Well, it's just going to be the 2 and the 3. Now, sometimes you'll try to take the intersection of sets and there's nothing in common. So there are no elements in common, so the set you're going to get is going to be empty. Or we symbolize that empty set like that. So when there's nothing in common between the sets, and you try to take an intersection anyway, you're just going to get the empty set. So what we're going to be interested in are unions and intersections of intervals. So let's consider two intervals. -3 to 0, and let's go -1 to 2. Now we include those numbers. If we're going to look at intersections and unions of these sets, sometimes it helps to draw a picture of what these intervals are doing. So say we have 0, 0, 1, 2. -1, -2, -3. 1, 2, -1, -2, -3. Now, in this first one, we're talking about this. Numbers from -3 to 0, but we don't include 0. We don't include -3. For this other interval, we have -1 to 2, but we do include -1 and 2. So let's look at the union. Well, if we take all the numbers from here and dump them into a box, and the numbers from here and dump them into a box, what we're going to get? Well, the question we're going to ask is, what numbers do we end up getting? Well, for this first interval, we're going to get all the numbers from -3 to 0. So we're going to get those. But we don't get 0, we don't get -3. But then, when we take the numbers from this set, or this interval, and dump them in, we're going to get all the numbers from -1 to 2. So we're going to get all of these. Now notice, we also get 0. So we can get rid of this little parenthesis, because this will contain the 0 that we're missing in that interval. And this will also have the 2. It'll have the -1 also. So what we end up getting when we do the union is an interval from -3 to 2. Oh, and sorry, I used the wrong one here. Those are brackets. When you union these two intervals, this is what we're going to get. Now, what if we take the intersection? Well, the intersection is only where these intervals overlap. So where do they overlap? Well, it looks like they overlap from -1 to 0. So that means they're overlapping here. And then it looks like we get to keep 1. because 1 is in both of these intervals. But we don't get to keep 0. 0 is in this interval, but it's not in this one. And again, intersection means it has to appear in both sets. So we're not going to be able to hang on to 0. So what this means, -3, 0 intersect -1, 2 is equal to -1, 0. And that's going to be our answer. So let's take a look at some other ones here. Now, let's say we've got this. This one. We'll exclude the 5. Come on, let's go with 8. We'll exclude the 8. So let's look at the union. So if we think about the union, we're combining these sets. So the first set, we have 5, and it's just going to be all the numbers on down here. So that's what this one looks like. Now for the second set, it's 1 to 8. So 1 is going to be smaller than 5. Let's say 1's right here. 8's bigger than 5. So say right here. And we're including 1. And we're excluding 8. So that means we get to keep all the numbers from 1 to 8. And well, we're including 1, but we're excluding 8. Now, in this other one, we excluded 5. And for this one, we included 1. Now, 1 is in this set, as it is here. So I don't need to mention this. It's already there. Now, this set excludes 5. So it looks like we're not going to be able to have 5, but this set contains 5. So we get it back. So we can get rid of this. And then we have all the numbers beyond 5 up to 8, then we don't include 8. And so that means this will be our answer. I'm going to try that again using the sort of drawn out method I used last time. So for the method I used last time, I have a number line for each interval. Put 5 here, and we'll put 1 here, put 8 here. Now, for this one, we exclude 5, but we want everything below it like so. Now, this one, we want numbers between 1 and 8. We've got that. We're going to include 1, but exclude 8. So now let's combine these intervals. So if we bring these together, if we put them all in the same box, we're going to have all the numbers up to 5. So we definitely have this. And it looks like we're excluding 5, but we're going to get the 5 back between 1 and 8. And then we get to go beyond 5 up to here, which is 8. But we exclude 8. And so when we look at the result, we're going to get the same thing. Negative infinity to 8. So that's looking at the union of this. What about the intersection? What numbers do these two intervals have in common? Where do they overlap? Let's do that. So looking at where these overlap, it looks like in this area. So this is where they're overlapping. And it looks like we're overlapping between 1 and 5. So this is our region of overlap. Now, the next questions we need to answer are, do we include 1 or exclude it? Do we include 5 or exclude it? Well, it looks like 1 will be in both of these intervals. It's already included here. It's just taken for granted that it's there. Here, it's a boundary, but it's an included boundary. So in both sets, we have the number 1. Whether it's an included boundary or it's just assumed that it's there. So we're going to get this. Now let's look at 5. Now 5 is here. It's taken for granted that it's part of this interval. And here it's a boundary, but it's an excluded boundary. So 5 isn't actually here, even though it is here. But with intersection, we only want numbers that appear in both intervals, not just one. That means we're going to exclude 5. And so our answer that's it. So that's sort of an introduction to working with union and intersection of intervals. Now let's take a look at some problems with inequalities. So basically with inequalities, when we solve these, we use the same techniques as solving equations. Same techniques as solving equations with one caveat, except it's not really an exception. The techniques are going to be the same. There's just an added piece to this. Multiplication or division by a negative number. It flips around the inequality sign. And it's only multiplication, it's only division. Addition and subtraction of negative numbers is totally fine. It doesn't change anything. It will not flip around the inequality sign. Only multiplication and division of negative numbers. If you multiply and divide by a positive, it won't affect the inequality sign. But if you multiply and divide by a negative, it will. So that's the one difference we're going to keep an eye out for. Also, another thing is that the answers you'll get, you're going to get intervals for solutions usually. Sometimes you get an empty set. So those are the big differences. So let's take a look at some of these. So let's say you have 3x is less than 12. Well, you do the same thing as you would if this was 3x equals 12. Divide both sides by 3. You'll get x is less than 4. And that is your answer. And you could graph this on an interval if you wanted to. So 4, x smaller than 4, all the numbers down here. And since this is, there's no equal to, it means we leave out the 4. All right. Now, let's say we have this, though. Negative 3x is less than 12. And let's put an equal to in here, just to have some variety. Well, again, divide both sides by negative 3. But because we divide by a negative, this flips around to become this. Now, 12 divided by negative 3 is negative 4. But this flips around because we divided by a negative. So that's our answer. What the interval looks like, negative 4, everything bigger than negative 4. And since we have an equal to, we'll put a bracket. And there we go. All right. So again, what we're going to do, we're going to solve for x just like we would with an equation. Subtract 5 from both sides. Divide both sides by positive 2. So we get x is less than 6. And if you were to graph this, it's going to look like that. All right, let's try another one. So again, solve for x like it's an equation. We'll first add 7 to both sides. We have 3x less than or equal to 20. Divide both sides by positive 3, so we're not flipping anything around, so positive. X is greater than or equal to 20 over 3. And again, if you were to do a graph of this, gives you 20 over 3. What is that? 6 2/3. And that's going to be your answer. Let's do another one. Now, let's say we have something a little more complicated. Now, again, the trick with something like this, we can multiply through by either a lowest common denominator or a common multiple. What that does is we want to cancel these denominators. So what could cancel a 6 and a 12? Well, again, we could use the LCD method. We could just come up with a number that's divisible by 6 and 12. The easiest number? 6 times 12. Well, it's actually maybe an easier one, to be honest. It's going to turn out to be 12. 12 will divide into itself, and 6 will divide into 12 also. But if you had some number like 17 times 15, or 17 and 15, you can multiply through by 17 times 15 and cancel where you needed. Either way, you're going to get the same answer. In fact, even though that's kind of a burdensome technique, I just want to run through it. You can multiply through by 12. That's actually the easiest thing to do. But let's say, or we don't see that option. So let's say we have this. We're going to use a common multiple of 6 times 12. So what we'll do, we'll multiply everything through by 6 times 12. And again, because this is positive, it's not going to flip around that inequality sign. So we'll distribute this common multiple. And now we're going to look for cancellations. 6 above, 6 below, kind of like reducing fractions. Those will cancel. Nothing to cancel here. And then a 12 above and a 12 below, those cancel. And so we've gotten rid of those denominators. So what that gives us, and so now we have a problem without denominators, and that just makes life easier. So we'll distribute this through. So 12 times 4 is 48. Minus 36. This will be 144. This will be 12x minus 6. Do we want to combine like terms? Let's subtract 12x from both sides. We'll get 36x. And then this is negative 36 and this 144. Let's see, it's going to be 108. Just check my arithmetic. It is in the morning, so I want to make sure I haven't made a mistake. So 144 subtract 30 will be 114. 114 subtract 6 would be 108. 108. So we're good. And then we're going to subtract 108 from negative 6. So that's going to give us 36x is greater than or equal to negative. Oh, we go back to 114. Finally, we divide both sides by 36. And you know, grab a calculator just to make sure that's going to be okay. All right. So we'll get x is greater than or equal to, well, I just get negative 114 over 36. Let's see, can we reduce that down? Well, they're both divisible by 2. So that's going to be 57 on top and 18 on the bottom. And a little trick you can do, if you add the digits of numbers and they add up to something divisible by 3, this is just a trick, then that number is divisible by 3. So you look at 57, it's like, I don't know. But 5 plus 7 is 12. 12 is divisible by 3. So that means this is divisible by 3. Well, 1 plus 8 is 9. 9 is divisible by 3. And we know 18 is divisible by 3. 6 times 3. So divide top and bottom by 3. What do we get? All right, I'll bust out a calculator for 57. 19. Now 19 is a prime number. 18 divided by 3 is 6. And so there is your answer. All right. That's good. All right. So let's take a look at another one. Now, sometimes you get unusual solutions. For example, x plus 1 greater than x. If we think about this, what this says is that a number plus 1 is always bigger than its original self. So that means 5 is always bigger than 4. 3 is bigger than 2. Well, that's always true. I mean, we can try solving. We subtract x from both sides. We'll get 1 greater than 0. And that's always true. Doesn't matter what number we choose for x, this is always going to be the case. So the answer here is all real numbers. And the way we express this in interval notation negative infinity to infinity. So you could get results like this. And what will happen is if you cancel your x's, you're going to get some numerical inequality that's just true. It's like the x's have disappeared. We didn't want that to happen, but they did. You get something that's correct. 1 is greater than 0. Answers are all real numbers. Now, sometimes it doesn't work out quite that nicely. Let's say we have this. So again, we're going to distribute here. So we'll get 3x minus 24 minus 2 times 10 is minus 20. Minus 2 times minus x is plus 2x greater than 5x minus 5. And so let's combine some like terms on this side. 3x plus 2x will be 5x. Negative 24, subtract 20, it's negative 44. You get 5x minus 5. So let's say we subtract 5x from both sides. We'll get negative 44 is greater than negative 5. Now, positive 44 is bigger than positive 5. But negative 44 is smaller than negative 5. And again, this has to do with the number line. Negative 44 is to the left of negative 5, which is to the left of 5, which is to the left of 44. Negative 44 is not greater than negative 5. So this is where you have no solution, which means there's no real number that will make this inequality work. Or the way we express this, the empty set. So that could occur also. All right. Now, another kind of inequality you could get is what's called a compound inequality. And you could have something say like this. So it could be given to you as two inequalities with an and. The and's got to be there. What it's saying is this. This has to be true, and this has to be true. So what we're actually looking for, we're looking for numbers that satisfy this and numbers that satisfy that. So the numbers have to satisfy, I'm going to reword that a little differently. We want numbers that satisfy this and also at the same time satisfy that. So the numbers have to accomplish two things at once. They have a number that's going to be a solution to this type of problem will work here. It will also work here. So in a sense, what we're looking for is an intersection. We want numbers that appear in both of these solution intervals. Now you might ask, well, okay, but what if we want numbers that can do this and also the numbers that can do this, and we don't care if they can do both at the same time? Well, there is such a thing, and you change this from an and to an or. But we're going to be looking at the and. So we want that narrow group of numbers that can accomplish this at the same time they can also accomplish that, not just one or the other. So the way we typically express this, we rewrite this. We want numbers x, where if we plug them in here, the result will be between 3 and 19. And we're allowed to include the number 3. This is called a compound inequality. Compound inequality. So what we're going to do, we're going to solve for x in the middle. And what we do to the middle, we do to the sides. we do to the middle, we do to the sides. So let's go about solving this. So first off, we want to isolate x. So let's add 3. If we add 3 to the middle, we have to do it to the sides. So that means we do this. And we get 6 less than or equal to 4x less than 22. Then we divide by 4. And because it's a positive 4, it doesn't switch around the inequality signs. Now, if this was a negative 4, dividing by everywhere by negative 4 would switch this around, and it would also switch that around. Anyway, what we'll get is 6/4, 22/4. And we can reduce these. This will be 3/2 less than or equal to x less than 11/2. And that's going to be our answer. Now, what we can do is, let's write in my hand. You can also graph this. So there's 3/2. There's 11/2. 3/2 is 1.5. 11/2 is 5.5. So we want the numbers certainly between 3/2 and 11/2. But we get to include 3/2. But we exclude 11/2. We don't quite get to 11/2. And that would be our answer on an interval. All right. Let's see. So let's take a look at one like this. So let's say we have something like this. Again, we want to solve for x in the middle, so let's add 2 everywhere. So we get 6 less than or equal to negative 3x less than 12. Now divide everywhere by negative 3. Because we're multiplying or dividing by a negative, we got to switch things around. Now again, if you add or subtract negatives, that's perfectly fine. That doesn't change anything. Multiplying, dividing by positive numbers doesn't change anything. That's perfectly fine. But multiplying and dividing by negatives, that's going to switch these around. So what we'll get, negative 2 greater than or equal to x greater than negative 4. Now, typically we write this where the larger number is on the right and the smaller is on the left. So we'll typically rewrite this like so. Smaller, larger. So larger is on the right, smaller is on the left. And if we graph this, we're not going to include negative 4. We are going to include negative 2. And that's going to be our solution. All right. So the last thing to talk about in this section are absolute values with inequalities. So what we're going to do is consider two types of problems. And you can have an equal to. It's not going to change anything other than you have an equal to there. When you get this type of problem, what you're going to get is this. You're going to solve that version. But when you get this one, this is where that or comes in. You'll solve this, and then you'll solve We'll solve that one. And the reason is, and let me give you an example of why it breaks down this way. Let's say we have x, absolute value of x greater than 5. Well, first off, numbers like 6, 7, 20, 800. If you take the absolute values of these, you're going to get numbers bigger than 5 because the absolute value of a positive number is a positive number. So these are all, you take the absolute value, they're bigger than 5. But let's think about this. What if we took -6, -7, -20, -800? Well, these are smaller than -5. But if we take the absolute values of these, we're going to get positives. They're going to be bigger than 5. So if we took the absolute value of these, this will become 6, this will become 7, this will become 20, this will become 18. And those absolute values will also be bigger than 5. So when we solve this one, we want numbers bigger than 5, but also numbers that will work will be less than -5. Because -6, take the absolute value of -6, it's going to be bigger than 5, for example. So just want to talk about that one a little bit. This one, this is where you're going to get the and. And what ends up happening is you want numbers, the absolute value of this number is, say, smaller than 3. So let's say we have absolute value of x is less than 3. So numbers that work right away, 1, 2, those work. Absolute value of 1 is 1. That's smaller than 3. Absolute value of 2 is just 2. That's smaller than 3. Same with -1. Absolute value of -1 is 1. That's smaller than 3. Same with -2. Absolute value of -2 is going to be 2, which is smaller than 3. But what if we brought in the number 4? Well, the absolute value of 4 is 4, and that's not smaller than 3. It's bigger. We get the same problem with -4. Absolute value of -4 is positive 4. Again, absolute value makes everything positive. And 4 is still bigger than 3. So we can't use -4 and 4. So what we end up finding out is that we can use these work, 0 will work, but that won't. Same with like 3.5. 3.5 isn't smaller than 3. -3.5, you take the absolute value, you get 3.5. Again, not smaller than 3. So negative 3.5 won't work. 3.5 won't work. Take 3 itself. Is 3 smaller than itself? Nope. But you could take negative 3, right? Well, absolute value of negative 3 is again 3. 3 isn't smaller than itself. It's not going to work. But you could do 2.9999. 2.9999 is less than 3. So that's working. Negative 2.9999. Take the absolute value. It's now positive 2.999. And that is still smaller than 3. So that works. What we ultimately figure out is this. We can use any real number x, provided it's smaller than 3, and it's bigger than negative 3. And so that's why we set this one up like that. Anyway, let's do some problems. So let's say we have this. Now again, this is a type U. This is some algebraic expression less than some constant C. So that means we break it up into this form, which for us means negative 8, 2x minus 6, positive 8. And then again, we solve for x like we did before with a compound inequality. So add 6 everywhere. Divide everywhere by positive 2. That is going to be your answer. And as an interval, we take all the numbers from -1, 7, but there's no equal to, so that means we don't include -1, and we don't include 7. And that's it. All right. So let's see here. Let's say we have this. Now, what we want to do, let's solve for this absolute value first and then see what kind of type of problem we have. So add 3 to both sides. Divide by 5. So what we get is this. Absolute value of U is greater than C. Yeah, it's okay to have equality. That's all right. So this breaks down into 2 problems. 2x plus 1 over here. Let me show how it breaks down here. Will be U greater than C, and then U less than negative C. Or for us, 2x plus 1 greater than 12/5, or 2x plus 1, oh, I gotta have that equal to, because this one has an equal to. This will be less than or equal to negative 12/5. And in both of these, we're going to solve for x. So subtract 1 from both sides. So you can say 12/5 minus 5/5, 7/5. And then for this one over here, minus 12/5 subtract 5/5 is negative 17/5. Divide both sides by positive 2. We'll get 7/10 over here, negative 17/10 over here. Now, here's the thing. This is an OR statement. So we have really two collections of numbers. If there's a number that can satisfy this, it's a solution. Or if there's some other number that satisfies this, it's also a solution. This is not an intersection. This is not where we're looking for overlapping. We're not looking for numbers that can accomplish two inequalities at the same time. We're not looking for that in this case. For example, 100 is greater than 7/10. So 100 would be part of our solution. In this case, negative 100 is less than 17/10. That would also be part of our solution. So we'd have 100 and a negative 100 in our solution set. So this is an or a union, where the and was an intersection. We only want numbers that can accomplish both of those inequalities at the same time, not just one or the other. Well, in this one or the other is just fine. You could be in here, you could be in here. We're going to put you all together in the solution. It's a union. So what does this look like on a graph? Well, on a graph, well, we want numbers greater than or equal to 7/10. So here's all the numbers greater than 7/10, and we're going to include them. We have an equal to. And we want numbers less than negative 17/10, and we're going to include them. And so this becomes your answer. So we're not looking for overlap. It's this set union with that set. And that's it. All right. Now, sometimes with these, you'll get some unusual solutions. So let's say you have this. So how do we go about solving this? Well, we would do it the same way as before, but here's the thing. We're taking absolute values. It's making everything positive. Now, I do have to be kind of careful. I want to say as we did before. In fact, let me be a little conservative here. Something a little simpler. You have to be careful multiplying both sides by x. That's sort of the concern. What is that doing to your inequalities? So let's just go with something simpler. Because we're taking the absolute value, this is always positive. And because it's always positive, it's always greater than a negative, no matter what. So no matter what we choose for x, it doesn't matter what this becomes in between the absolute values will make it positive. So what this means, it doesn't matter what you choose for x, it's always going to end up at the end greater than 0, or maybe equal to 0. But certainly greater than negative 2. So this is another all real numbers. Absolute values are always going to be bigger than the negative numbers. Another one you could see, again, it doesn't matter what you choose for x. This is always going to be greater than or equal to 0 once you take the absolute values. Could something greater than or equal to 0 ever be less than -1? Well, it can't. So that means there's no x we can choose that's going to make this negative. Well, it can make this part negative, but then that gets turned into a positive. So what we get, this is impossible. This can't happen. So the answer is no solution for the empty set. So that's it. That's section 1.7. If you have any questions, let me know. Other than that, have a wonderful day.